Alright, ladies and gentlemen, this is Mark Anderson for Kellogg Community College, and we are going to be looking at graphing quadratic functions in this first of two-part video. We're going to look here at three different parabolas which have a values that are positive, and to remind you a little bit about what I mean by a values is that the quadratic function itself is ax squared plus bx plus c equal to y. Or, as we've seen it in previous chapters, we've seen ax squared plus bx plus c equal to 0. And I say that because in those previous chapters we were looking to see when does this parabola cross the x-axis. And we set that equal to 0 because that would be the height at that moment. Also, casually I've said, when does the graph hit the ground? Because the parabola would cross the x-axis at 1, 2, or 0 places. But we're going to set this equal to y, or f of x, and this is essentially going to be our quadratic that we've used for, in previous videos, the quadratic formula. But we're going to talk a little bit about what these letters mean and stand for. The a value, otherwise known as the amplitude, is useful in figuring out whether this is going to be a smile or a frown from a graphing perspective. So if the a value is positive, then it's going to be a smile. And if the a value is negative, then it will be a frown. And if the a value is ever 0, then it would be a linear equation. Now, part C is handy. If we know about the letter C, this is going to be our y-intercept. And that's because if I plug 0 in for my A and B, what this gives me is 0 for my x's, which means that my x is going to be, basically this is going to be on at the origin on my x, and then the height of y is going to be at that value of c. So therefore c is the y-intercept. Now the vertex is going to be based on b a little bit. The vertex is negative b over 2a for my x value, and then f of negative b over 2a for my y value. Now what this means is that I will find my vertex by taking my b and using its opposite value and then dividing it by 2 over a to find out what my x value is, and then I will plug my x back into my function, or f of x, and that will give me my y value. And this is why when you see equations like f of x is equal to ax squared plus bx plus c, it's synonymous with just saying y equals ax squared plus bx plus c, because the value for y is whatever you plug in for x into that function, and that you get that value for y. So f of x is y, and that's why this equation is to find your x value, negative b over 2a, and then f of negative b over 2a. So essentially what I'm going to do is I'm going to teach you about graphing these problems. We're then going to label the vertex, the axis of symmetry, and then talk about the domain and range. I'm going to also show you how to do some calculator tricks, so if you happen to have your graphing calculator with you, that would be fantastic. More importantly, I will also circumvent this vertex formula and show you the shortcut on the calculator, which would be kind of useful when you get to some of the harder problems where the vertex isn't actually shown very easily on the graph or the table. So let's move down a little bit to our first example here. We're going to graph x squared minus y, and I'm going to bring up my calculator, and I will type, and first of all, it's probably useful to say that there are some things that you should do to set your calculator up to help you with graphing this. Since I kind of know where this is going to go, let me kind of put the calc here. Now, I would suggest that you go to a clear screen. Make sure it's nice and clear. Hit the clear button a couple times here. Go to your y equals and hit clear on that. Make sure there are no equations in there and nothing in the plot 1. Also, I would go to zoom and click on 6 so you get to a nice clear screen, and make sure there's no dimension mismatch errors or anything like that. And again, things you want to check, make sure nothing up here is black or highlighted. Again, your zoom 6 will get you back to a standard window, and everything we should see here we're going to be able to plot here. In fact, I do have to move this down a little bit, and let's remember the equation is x squared minus y, and I'll rewrite that because I know we have to go to the very bottom here. So let me bring the calculator back up. Let me also remind you that we're going to look at x squared minus y, and let's type that in. So click on the y equals, and then type in the x squared minus y, and let's look at the graph. So this graph is going to be here on this page. I'm going to transfer this to this, and I'm going to do so by looking at the table. Now, the vertex of this graph is the lowest point on our parabola. When we have a smile, and I will freeze the calculator right here, when I have a smile, the vertex is going to be at this, the vertex is going to be at this lowest point. It is the point at which the parabola changes direction. And if we look for that minimum point, because the equation again, y is equal to x squared minus 9, is going to have a minimum. And we can see that minimum right here on the calculator. And that minimum is going to be that y value, and that x value, this is here, this is my vertex. And what I'll do is put my vertex here, and that's going to be the point 0, negative 9. So that's my vertex, and I'm going to put that dot now right there. And I'm also going to want to graph this. Now I do have some stipulations for my students for graphing, and my 5 mandatory points includes the vertex, 2 points on the left and 2 points on the right. And I'm going to choose symmetrical points on the left and the right. So negative 1 goes down to negative 8. That's the comma negative 1 comma negative 8, and negative 2, negative 5. So there's my 2 points on the left, and on the right they are symmetrical, negative 1 to negative, or positive 1 to negative 8, and positive 2 to negative 5. All right, and now I create my curve like so. This is my parabola, and I have 5 point minimum. You can plot more, but this is what I'll be checking on my homework if you're one of my students. So what else is there to do? Oh yeah, we have to talk about the axis of symmetry. The axis of symmetry is the line that would bisect this graph and make a complete mirror image from one side to the other. This axis of symmetry cuts it in half, and the left side and the right side do fold on each other, and this would be the equation of that vertical line. In this case, it's x equals 0. The domain and range is created by how wide the graph is, and the range would be what's its lowest to highest part. Now we're going to use set notation here, and for the domain I'm going to kind of do a shortcut, because the domain goes as far left as you can imagine and as far right as you can imagine. As the graph approaches infinity in either direction, it will get wider and wider, so my domain is going to be all real numbers. I'm just going to leave that outside of the set notation just because that's easy to understand. The range, though, does not go to positive infinity to negative infinity, because see, there's this floor here. This minimum of negative 9, the small spot right here, the graph will not get any lower than that. And so, since the graph will not get lower than that, we're going to use our set notation of our little Alfred Hitchcock bracket. Y is knocking on the door, and y is going to be greater than or equal to negative 9. Because we can see that there is going to be no value lower than that negative 9, and y values above negative 9 and including negative 9 will be possible. So that is our 5-step process. We're going to graph the equation, we're going to investigate the table to see if we can find that minimum, and if that minimum is findable, we will call that our vertex, and then from the vertex we can get our axis of symmetry, our domain, and range. Now, a couple of you pattern finders in the room will find the pattern probably by the time we get done with this next problem. I'm going to erase my material here and start over with this equation, x squared plus 4x. So I just do a small modification to the original equation I typed in there and take a look at the graph. All right, looks like the graph is going to be primarily on the second and third quadrant, with a little bit on the first. So if I move my graph over here, I should have enough room to write. Now let's go and see if we can find that minimum point right down there at the bottom. Now I will look at my table and see if there is a minimum point on my y, and there definitely is. Now these examples are pretty easy. In fact, we're only going to be looking at these minimum points on the calculator, and I will be using the equation that negative b over 2a as a kind of a check, and I want to do that for the previous two problems in a row. But let's go through and see what we can do here. I'm going to freeze the calculator. Now I'm going to take a look at my minimum value, which is this point at the -2, -4. That -2, -4, which I will now put down as a dot there, and that's going to be my vertex. So -2, -4. And now I'm going to talk about my axis of symmetry. My axis of symmetry is going to be cutting this in half. To see this a little bit better, I'm going to put two other points on the left, -3, -3, and -4, 0. And on the other side, we're going to go -1, -3, and the origin at 0, 0. So this makes my beautiful parabola that moves off like this, and my axis of symmetry would go straight down the middle, cutting it in half, and that axis of symmetry is the vertical line of x equals -2. Now my pattern finders might say, well, isn't your vertex answer here the same as your x value here? Will that be that way all the time? And the answer is yes. For vertex is going to be in the middle, which will create our axis of symmetry place, and that x value will be shared. Now if we talk about the domain of this graph that gets infinitely big from left to right as it approaches to infinity and negative infinity is going to be real numbers as well. And you might then think, well, is this going to be always real for parabolas? And I would say for the time being, yeah, you can assume that, because these are going to be smiles or frowns of degree 2, and that is going to be that characteristic. We're not going to see anything different like that until we hit the logarithm chapter, which is going to be in about a week or so. Now, the range is going to be basically how, tall and low this line will go, and it does go to infinity, but it does hit the floor at -4. So we'll use our little Alfred Hitchcock symbols here, and we're going to y such that y is going to have to be bigger than or equal to -4. And we can see that in our picture here, because the y values can go anywhere to positive infinity, but it cannot go any lower than this -4. It's kind of our floor here. So now you might be thinking, well, according to our vertex, will these numbers always match? And the answer is yes. But I will, give you a little warning once we get into graphs where they're frowns instead of smiles, or where the first value is a negative. You would have to switch the symbol here, because we're going to have a ceiling instead of a floor. But now this whole -b over 2a thing. You saw me actually do the vertex based on the calculator, but what if you're not sure? Now let's go back and remember that our previous equation was y equals x squared minus 9. And the equation was -b over 2a, and then f of -b over 2a. And that looks like a 6, but it should be -b over 2a for the y value. So let's actually explore this a little bit. My a value is 1, my b value is 0, there is no x value in this equation, and my c value is -9. So what I'm going to do is use this -b over 2a to figure out what my vertex place is. And so I'm going to take my -b, which is -0, divided by 2 times a, which is 2 times 1, and I get -0 divided by 2, which is 0. So here's my vertex for the first problem at 0 on my x. And to figure it out for my y, I'm going to plug the 0 squared minus 9, and 0 squared minus 9 is equal to -9. And so there's my vertex for the first problem. And you can actually go back into your notes and see that that was the vertex, but we used the technology. Now, how does it fit for this problem, where my a is equal to 1, my b is equal to 4, and my c is equal to 0? Well, you're going to see we're going to get -2, -4 if I plug -b over 2a and these numbers into each other. So -b, which is -4 over 2 times a, which is +1, gives me -2. Oh, wow, that's my x value for my vertex. Now I plug that -2 into this equation, which is going to be -2 quantity squared plus 4 times -2. So I get 4 minus 8, and because -2 squared is 4, 4 times -2 is -8, and then 4 minus 8 is -4. Oh, look, there it is. there's the vertex. So what's kind of handy here is that we can actually use the negative b over 2a and the f of negative b over 2a to find the vertex. But the calculator can do this too, so let's use the calculator as much as we can, but if we're needing to show our work, there's the little work for showing negative b over 2a. Okay, so our final problem on this page for part 1 of the video here, we're going to tackle a problem where the vertex is not showable on the actual grid that well. Now, I'm going to kind of move the, whoops, hold on. I'm going to move the calculator over here. Let me see here. It will just creep in on the calculator. Okay, cool. So now I've got my plots on. I'm going to type in x squared minus 3x plus 2. Oops, I forgot my x. Insert an x. All right, so now I'm good. Let's take a look at that graph. All right, let's go and see where that vertex is. And since this is a smile, I'm looking for its low spot, and here's the problem. You'll note that there is no low spot there. Well, that's a problem because I can't actually see based on the table where the vertex is. So I'm going to do something here. I am going to choose on either side of this calculator. I'm going to make a plan. One plan for the negative b over 2a, and the other plan is going to be to help me out with doing the vertex based on a calculator trick. And I want to show you first of all the negative b over 2a. And I'm going to do it on the technology so you see how nice it can work out if you have a nice clean screen here. So negative b is technically negative 3 divided by 2a, which in this case is going to be 2 times 1. So this right here is your x value. Okay, and we're going to write that down as our x value for our table. We're also now going to go to, and let's actually just check. Does it look like that vertex is at 1.5? And it sure does. All right, so now what we're going to do is go back to this screen, and I'm going to plug that 1.5 into my problem, and I'm going to use the answer function, or I could just type in 1.5 by going second negative, though. I can pull that answer up and take that 1.5 and plug it back in for every instance of x, and that's going to give me my answer, which is great because in case your number here is a larger decimal, this would include all the decimals in there without having to do any weird rounding, and there you have your final answer for the y value of the vertex at 1.5 and negative 0.25. Now let's look at the graph and see. Yeah, that seems about right. At 1.5 and negative 0.25 on my x and y respectively, that looks about right. So what I'm going to do now is then use the calculator to get me the rest of those points. So before I forget, this is going to be at the vertex of, and this the vertex was at 1.5 and negative 0.25. So that right there is going to be about here. Looks like there's a dot between the 1 and the 2. And I'm going to use these points here to finish up my 5-point minimum criteria. So 1, 0, 2, 0, and then 0, 2, and then 3, 2, and let's make our parabola like so. All right, and there it is. There's our vertex, our axis of symmetry. Our axis is going to be where x is equal to 1.5. So halfway between the 1 and the 2. Oh man, hard to draw a straight line sometimes on this pad. So x is equal to 1.5. So there's my axis of symmetry. Oh, what's next here? Oh yeah, my domain is going to be real, and my range is going to be where y is knocking on the door. In the y has to be greater than or equal to negative 0.25. All right, and that's going to be that. Now, I want to show you now, for the last part of this video, a cool calculation command using the trace button. So here's what's going to happen. I'm going to have to clear all this off, but I'm going to get that 1.5 and negative 0.25 or close to it using the calculator. Now, you'll note that the calculator has a trace button, and if I click the trace button, all it does is just kind of lets you kind of move along the line, which is neat, but I mean it doesn't actually give us, and if we try to find that low spot right there due to the zooming of the graph, I mean we can get close, but it's just, you know, it may not be as accurate as we want it to be. So I want you to go to second trace. And what I do when I go second trace, it brings up this menu, and what I can do is I can find the minimum, or that vertex on that parabola. So if I hit enter on minimum, it's going to ask for the left bound. Now what I need to do is bring my cursor to the left side and hit enter. Now what that does is it creates kind of a little stopper or a wall there, and it basically is going to look to the right of that spot for the smallest part of your parabola. Now we're going to go to the right bound, and I want you to hold down the right arrow key, and that left and right arrow key is how you move from along the line. And I'm just going to move over to the right. Now you might be wondering, like, should I have gone exactly to the same amount of spot? But you actually just don't need to be exact. You just need to be on the right side of wherever you guess where the vertex is. Now the guess spot is where you think the vertex is, so you're going to get it as close as you can and hit enter, and then it's going to do some calculation and get pretty darn close. There will be some rounding you'll have to do because these pixels aren't, exactly microscopically small, so the technology is going to get, a little off sometimes. But if you do your normal rounding, or reasonable rounding, you will get to the vertex, which we had found by using the formula of -b/2a quite nicely. And I think there could be some pushback on, like, well, why don't you just use this trace command all the time instead of looking at the graph and looking at the -b/2a? And it's not as accurate, I would say, but in a defense of this method, later on in the unit, we're going to be looking at some very complicated parabolas when dealing with quadratic regression, and we're going to want to find peaks and valleys, and we're going to have to get extremely accurate with data that wouldn't be so easy to plug into -b/2a. So I do want to teach this trace technique, as I will further review it in the next video, but I'm hoping that you find that all of these techniques can be employable by yourself, with or without technology. So thank you very much for watching, and part 2 is coming up with 3 more problems, including one example with a -a value, so we will see a frown in the next video. Alright, thank you very much for watching.